This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question AB5, namely rectilinear or straight line motion. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here is an outline of the information presented in this video. I'll start by briefly discussing some background information associated with straight line motion problems and the AP Calculus exam. I'll then mention some preliminary facts about particle motion problems that students need to know in order to begin any of these problems. Then I'll present some common terminology used in these types of problems and how these key words and key phrases are translated into mathematics. And finally, I'll present and solve a calculator-active particle motion problem with many parts, utilizing several AP Calculus concepts. First, a little bit of background information. Particle motion problems occur frequently on the AP Calculus exam. There is a free response question concerning particle motion almost every year. And specific particle motion concepts are also tested in the multiple choice section of the exam. The questions related to particle motion often involve the fundamental theorem of calculus, or net change theorem, displacement, total distance traveled, and the speed of the particle. And many of these questions are calculator active. I think there are just a few basic facts that a student needs to know before they begin any of these problems. Let's suppose a particle moves along a horizontal line so that its position at time t is given by the function s of t. The velocity of the particle is the derivative of the position function, and that is v of t is equal to s prime of t. And the acceleration of the particle is the derivative of the velocity function, or the second derivative of the position function. And that means that a of t is equal to v prime of t, which is equal to s double prime of t. Here's a list of some common key words and key phrases as they might appear in particle motion problems. And alongside each is a mathematical translation of each of those key words and key phrases. Let's suppose the question includes the phrase, "the particle is at rest." Well, that gets translated into mathematics as the velocity is 0. The phrase moving to the right or moving to the left means that the velocity is greater than 0 or that the velocity is less than 0. The phrase average velocity of the particle on the interval a to b gets translated into this definite integral expression and is simply the difference in position divided by the difference in time. Suppose we see the phrase the velocity of the particle is increasing or decreasing. Well, that means we need to find those times where the acceleration or the derivative of the velocity is greater than 0 or less than 0. The speed of the particle means we need to examine the absolute value of the velocity. The total distance traveled by the particle over the time interval a to b gets translated as a definite integral from a to b of the speed, or the absolute value of the velocity function. And finally, the displacement of the particle, or the net distance traveled by the particle over the time interval a to b, is a definite integral from a to b of the velocity function. Let's see if we can apply some of these calculus concepts to solve a problem. In this example, a particle moves along a horizontal line. And for t in this interval between 0 and 8, the velocity of the particle is given by this function v, and the position is given by an unknown function s. And we also know that s of 0 is equal to minus 5. Let's start by finding all the values of t in the interval between 6 and 8 for which the speed of the particle is 10. And then let's write an expression involving an integral that gives the position s of t, And let's use that expression to find the position of the particle at time t equal 4. In part C, let's find all the times t in the interval 0 to 8, at which the particle changes direction. And finally, let's find out if the speed of the particle is increasing or decreasing at time t equal 4, and let's make sure I provide a reason for this answer. Now I think this is a very good representative AP Calculus exam type question. There may be more than 9 points here, but each part is standard and often asked. In addition, this is a calculator active question. You could probably figure that out by looking at the definition of the function v. We can't find a closed form antiderivative for v, so we can't find an explicit expression for the position function. Yet in part B, I need to find the position of the particle at a specific time. In part A, we know the speed of the particle is the absolute value of the velocity. So conceptually, we need to solve the equation the absolute value of v of t is equal to 10. Now again, I can't solve this equation for t algebraically. So using technology, I decided to first explore this equation graphically. So I graphed the function v and the lines y equal minus 10 and y equal plus 10. And it appears that there are at least 2 values of t in the interval 6 to 8, where the speed of the particle is 10. Working on a graph page, I found 3 points of intersection. This graphical analysis suggests that there are 2 values of t between 6 and 8, for which the speed of the particle is 10. Now, one of my philosophies involving technology is to explore on a graph page, but confirm on a calculator page. So, on a calculator page, I used the solve command. And notice that using the TI-Nspire, I'm able to restrict the values of the solution to the interval 6 to 8. And finally, the speed of the particle is 10 at t equals 6.691 and t equals 7.603. In part B, here's a general expression for the position of the particle at any time t. The final position at time t is equal to the initial or start position plus the net change in position. And to find the position of the particle at time t equal to 4, I need to use technology. Here's a single mathematical expression for the position of the particle, and at time t equal 4, the position is 16.95. To find the values of t at which the particle changes direction, I need to find those values at which the velocity function changes sign. So I'll start by considering a graph of the velocity function. It appears there are 3 values in the interval 0 to 8 at which the sign of the velocity changes from negative to positive or from positive to negative. I found the 3 zeros of the function v on the graph screen. To confirm these results, I used the solve command on the home screen. The graph of v together with the numerical solutions indicate there are 3 values of t at which the particle changes direction. And these statements are generally sufficient justification or interpretation of a graph or a sign chart. To determine if the speed of the particle is increasing or decreasing at time t equal 4, I need to consider the sign of the velocity and the sign of the acceleration at time t equal 4. I used technology to find the value v of 4 and a of 4, which is the derivative of v evaluated at 4. Since the velocity and the acceleration have different signs, the speed of the particle is decreasing at time t equal 4. An interesting question to think about is, what's the speed doing if one or both of these values is 0? And a cool way to answer this question using technology is to find the derivative of the speed function directly. And that means the derivative of the absolute value of v evaluated at 4. Since this value is negative, That means the speed is decreasing at t = 4. I hope this video provides insight into AP Calculus particle motion problems and the use of technology. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.